This is the conservation of momentum lab, 151 and 251. There's a lot of overlap here. And so we're basically going to set it up over here and run through it. It is a lab. It is my attempt to have a perfect lab, and we actually have had some perfection in this lab. So this is my attempt at it. It's going to be a lot of starting and stopping because there's a lot of fine detail involved in this lab. So I'm going to stop it right now and pick it up in just a moment. All right, so we have a track here that I've set up. I've put the cart in 3 different spots and it doesn't roll, so we're going to consider that level enough. And also in terms of trying to go for perfection here, we have a triple beam balance. Notice it is not zeroed properly, so what I'm going to have to do is I'm going to have to add something to it to try to raise it above there, or at least get it close to 0. Sit a little bit below, so what I'm going to do is I'm going to add probably another sticky note, and then I'm going to stop this and come back with measurements. All right, I had to add basically that to it in order to get it above 0, and then that is what is considered the red mass. I'll sort of move over here. That is as lined up as my eyes can tell. Parallax can sort of throw that off, but so there's the measurement right there. That one right there that you see, let's see if I can hold this steady while I point. That one right there is 1 gram, and so this is less than a gram. So in the table, in table 1, and that's for both groups, the measured mass, that's with no carts on it. So it's measured mass with, I guess it's measured mass over there, and it's the red mass over here. And so what we're going to do is that is the offset. So we're going to basically, for all the following measured masses, we're going to subtract the value that we just had in order to get the actual mass. Actual mass is listed here, mass is listed here for 251. All right, so now I'm going to put the cart on it, and we will do it bit by bit. And so first one we're going to do is cart with plunger, and here is my cart with a plunger. Now the plunger is not needed for anything. The main reason we're using a plunger is because the magnets in this and the one without the plunger are set up so that we'll have an orientation where we can have a perfectly elastic collision, or what we hope is a perfectly elastic collision. So we don't have to unscrew anything and turn any magnets around. So I'm going to stop it until we get a new measurement for this. For cart with plunger, that's as lined up as I can sort of tell right there. We go, it snaps into focus. And so the values there were on the 10, the 500, and then you'll need to read that one to see where the widow's, hopefully that's focused well enough, so that you can get a sense of what the value is. And don't forget, you are doing it to the estimated digit here. Again, quest for perfection. All right, so that is the cart with plunger, and so now we'll do the cart without the plunger and the long load mass. Cart without the plunger, that's where it lines up. Again, that looks pretty darn close right there. Come on, snap into focus again. Well, there we go. And then the actual measurement, that's on 0, that's on 500, and that is the one that you're reading right there. So again, to the estimated digit. So basically look and see where the widow's peak is. And next the long load mass. All right, that's the load mass right there. And so give an idea of how well it's lined up. And then, so the top bar is on 90. The middle bar is on 400, and this one, again, estimated digit where the widow's peak is. And hopefully, let's see if I can stabilize my hands. That's slightly less shaky. And that's the long load mass. The lab is we basically have a motion sensor on both ends here. This is the hardest part of the lab. So what's going to happen is, they're right now measuring distances here. I want them to measure the same acceleration, because the issue I have with the typical momentum lab is you have a cart and you start rolling down the track and you assume that the velocity is constant. when in fact it's not. It is going to lose some because there is some friction into it, and especially I've seen this lab done with carts with bad wheels, in which case there's obvious friction involved. So what these are supposed to do is measure the acceleration, and therefore we can, from that, we can know how fast it's going just before the collision. Now, as it's going down there, these two should actually read the same acceleration. Just give a small little sample here of what it should look like. I'll put the cart, actually may as well start with the plunger cart because I believe the first trial is with the plunger cart. And put that onto it because that's going to be on it the entire time. It looks like I need to, oh, there we go. All right, so I'm just going to start this off. And as I look at this, why is it not showing anything there? Let's try that again. And I'm going to level the track. All right, so the track is leveled again, and so what's going to happen, just to give a sample of what's going to go on here, I'm just going to give it a small little push. Run it, stop it, and if you look at the two graphs here, notice that they're going away from each other, and I need to reorient some stuff, and I will. We have the sensor there on the left and the sensor there on the right. The one on the left is for the sensor number 1, so if I put my hand in front of it, I should get a small value for sensor 1 and a large value for sensor 2. And if you'll notice, try to eliminate the glare, we have a small for the first one and a large for the second one, and as that is as expected. Now I'm going to reverse sensor 2 here. So now that's negative. So now when I run the cart and we look at the trials, make sure it's in the groove. Now I run this. So notice now they are sort of matching each other, although they're a little bit off there. If you can notice, there seems to be a much more distinct curve for the second one than there is for the first one, and that's because they're not aligned. And so the big pain in this particular part of the lab is trying to align them. So now I'm going to go through the process. I'm going to the quick view of the process is I want that lined up so that the screen here is perpendicular to the track. And I come over here to make sure this one is lined up. That's looking perpendicular. That's a little bit off. And also I want that lined up. Now, if they are lined up, we should get the same acceleration from both. And I want them to be within, ideally within 10%. And so what I'm going to do is I'm going to now go through the painstaking aspect of doing it. And I've talked about how this is a huge pain in the butt, but however, I nailed it on the first try. So what I'm looking for in terms of acceleration is I'm looking for the coefficient of the quadratic term. The acceleration is twice that. So I got that value there and that value there. Let's see how close we are in percentage. I'm going to stop this, get my calculator. What I do not want to do is touch the table at this point. If I bump into anything and I'm recording, you will hear me cry. So I'm going to carefully back away and get my calculator. So I just did the calculations to figure out what the percentage difference is relative to the larger one. And I've already multiplied by 100, so it's 0.625% off. So that's the best I've ever seen. So, oh wait, actually there was a group that did nail it better than that. So that's one of the best I've ever seen. So what we're going to do now is try to run the lab without bumping into anything. This is the challenge, especially with one person, to stop everything, start and stop everything. So here we go. First thing we need to do, I guess we just ran the trial for the first cart, and there's the equation right there that is for sensor 1 and then sensor 2. Let me scroll here. And there it is for sensor 2 down here. I would expect A and B to be roughly the same. Would not expect C to be the same because that ultimately is the initial position, and obviously it's definitely a different position from both of them. So now we're going to do it for cart 2. Even if cart 2 does not have such incredible values like this, we're still going to not try to readjust it because that's just asking for trouble. If you are a masochist, then go for it. However, we're going to run it again with cart 2. I also want to point out that for cart 1, notice that the accelerations are negative, which is what I would expect acceleration to be negative because it should be slowing down. B is positive, A is negative, they're in opposite directions. And again, the A here is half of the acceleration. Here we go for trial 2. So now this is the one without the plunger cart. So I'm going to get it going. Try that again. I'm going to get it going. I stopped it recording longer than I intended to, but I'm going to stop this and get the equations. There's the equation for cart 1, and scrolling down, there's the equation for cart 2. The results are not as spectacular as they were for the first one, but we are still actually pretty darn good. It's about 6% off. Oh, let me scroll down just to get the RMSE value for number 2. So that's 2. And for those who blinked and don't feel like rewinding, I'm going to scroll for 1. And there's the equation for 1. So again, some pretty darn good results. The two graphs both curving the way I would expect. So I'm going to stop this and set it for the next part, which is the actual collision, I believe. All right, so I have cart 2 sitting right there and cart 1 plus sitting right there. In terms of the position of cart 2 at the moment, it is between the 58 and 59 centimeter mark on the scale here. Try to eliminate the parallax. All right, there we go. Eliminating parallax, so you can sort of pick that spot there. And for 151, one of the things I ask is how close does this get before it starts to interact? And for 251, that's been removed. So we're basically at what point there we go. And so give you a sense of where that is. And try to eliminate parallax there. There we go. So that tells you where that is between 63 and 64 centimeters, and you can pin down, estimate from there. So that's for 151. All right, so if we're actually doing the trial, we're going to roll cart. All we need is one really good trial. So far so good. And so what I'm going to do is I'm going to start the recorder, and motion sensor 1 is going to detect the motion of cart 1. Motion sensor 2 is going to detect the motion of cart 2. And so I guess I need to start this. I did stop it by hand, looking at the two plots right there. Looks like we've got a little bit of dirt in the track, but I'm not going to worry about that because the other results are so frickin' good. And you get an idea about where the interaction actually began. Somewhere in here, that's the point when cart 2 starts to move. And so cart 1 was cruising along, and then it interacts and then stops interacting. And this point right here, that's the point when I stopped the carts. And so anything past here is just garbage. Anything for basically for cart 2, that's the part we care about. Oops, let's see if I can. Well, hopefully you can. So cart 2, basically that's the part we care about. And for cart 1, we care about interaction before and after. So now it comes time for when does the actual interaction actually begin? So I'm going to stop this and start getting into the fine-tuned data here. Now I can bump the table. So I need to figure out when does the actual interaction start. And I can come up with an estimate here, but really what is of importance is what's in the data table. So I go over to the data table here, and I'm looking at this position 2 here, and it's basically oscillating back and forth between 0.428 meters and 0.427 centimeters. So it's obviously not moving yet. At this point, you notice it does start to move around here. And so that's the point when it stops being 0.427. So since it's obviously moving at that point, that is the last point at which it stopped. And so we're going to call that time 0. So at 1.88 seconds. And so the instructions at this point, if you read them carefully, are not too bad. And let me just get in close so you can actually read the numbers there. If you got some color blindness, then you can either email me or text someone. But the time is 1.88 seconds. The position 1, that's for cart 1, is 0.468, and position 2 is negative 0.427. Now, we don't have the same scale here. They have two different zeros between the two motion sensors there. And so we need to figure out a way, figuring that the interaction is going on as long as they are a certain distance apart. So when they first hit, cart 1 is still moving forward, while cart 2 starts to move away, but not as quickly. So they will get closer to each other, and then they'll get farther apart. So what I'm looking for is the point when they're farther apart than they are right there. And the way I was suggesting that you do it, and having gone through the math of it, I want to find the difference between those two, and then find the point in which the difference is greater than that. So I'm going to stop this, do the calculations on the side, and then come back and point out the values here. All right, so we have the data right here. I think I misspoke earlier. The interaction is taking place as long as the difference is greater than or equal to that initial value, which I got to be 0.895. In other words, 0.468 minus negative 0.427 is 0.895. And so after that, the difference becomes larger and larger and larger until you get to 2.04 seconds. And that's the point in which the interaction stops. That's when the difference is what it was before, and then the difference becomes less than that. So that tells you the beginning and end of the interactions. So conservation of momentum tells us the momentum before the interaction is equal to the total momentum after the interaction. And so what we're going to do is now do some curve fitting with those as our limits, and we will see what's going to happen here. So I'm going to stop this again and get the first set of equations going. To get the curve fit, what I need to do is I'm looking at cart 1 before the collision. I'm doing cart 2 also before the collision. And so I picked a time here, and let's figure out what the times are. So if you do analyze statistics for position 1, so I'm doing it from 1.3 seconds to 1.86 seconds. And so that's my curve fit right there. Now let's actually do the curve fit. Curve fit for cart 1. I want to do a quadratic fit, and there's the equation for cart 1. And stabilize, and you should be able to write that down. And then I want to use that same range right there, so curve fit for cart 2. Quadratic again, and that's it. Now, I would expect the acceleration to be really close to 0. It's not 0 exactly because of statistical fluctuations in the machine. You saw that it flipped back and forth between, within a millimeter of each other. So in the actual, when you do the calculations, there are two approaches to it. One, you can look at it from it's not moving, and therefore the initial velocity is 0, and I'm fine with that. Or you can use the equations to try to figure out what exactly is the initial velocity at that time of the interaction, which is 1.88 seconds. That's the beginning of the interaction, and you want the velocity at that time based upon this equation. And so I am going to stop this and figure out the post-interaction. Notice also, let me hit OK here. I tried to avoid the bumpy parts right here. I originally was thinking this could have been sand or some grit in the track. It also could have been my hand was still touching it at that point, and so I wanted to do it once it became smooth right there. So now I want to do the post-interaction. So we've already established it's sometime after 2.04 seconds and before I stop cart 2, so before that. So I'm going to stop this and get it highlighted. All right, so this is after the collision. Notice that the starting time is 2.12 seconds. And sorry about the shakiness here, but there we go, 2.12 seconds. That is the start of my highlighted range, and 2.7 is the end of my highlighted range. That should be enough data points right there. Matter of fact, it's 30 data points, so that should be plenty to get the curve fit. So let's do analyze, curve fit, and let's get rid of the old stuff. So curve fit position 1. So this is for cart 1, and we got the brackets there telling me what's actually going to be fit. And we want a quadratic fit, and that is the after collision numbers there. This is for cart 1. And now we do cart 2. And that is the after collision for cart 2 right there. All right, and we have negative value for A. If you double that, you get the negative acceleration, and since velocity is positive, which is one of the reasons for taking sensor 2 and having it reversed, so that velocity should be positive when it's going in that same direction. And so what we have here is, I think we have a good trial here. So I think that's it. For 151, you're done. 251, there is another part to it. Actually, you know what? I'm going to skip that second part for the sake of this video. And I think we are done. I do want to add the commentary that in the tables you're asked for when does the, so this is, I think it looks very similar between the two. For movement starts, movement stops, interaction starts, interaction stops. That's going to be should be the same for everybody. So we have that data right there. That was the 1.88 seconds and the 2.04 seconds. The movement starts should be the beginning value in the range when I highlighted, and I'd have to look at the video to remember what that is. I think it was 1.30 seconds, but I could be wrong on that. And then movement stops, that is the sort of the end of the highlighted range for this part right here. So if I hit cancel, that was the 2.7 seconds. So 2.7 seconds is when movement stops. Officially, movement actually went on past that, but in terms of what I want right here, movement stops at 2.70 seconds. And actually, I believe we need to get those values there, 2.7 for the chart there for position. So let's go over to the table. Go down to 2.7. Or actually, somehow 2.72 got included. Oh, I might have hit something else. So 2.7 is the one we care about right here. So 2.7, that are the two positions that we care about. This data over here is useless to us. We don't care about that data, but we do care about the position at 2.7 seconds. And just in case we did not get it, I'm going off of memory of 1.3 seconds. And if not, I will save the data, and then we'll be able to pull it up if we need additional information. Again, this data over here, we don't care about that data at all. But these are the ones we care about. Now I'll actually go check, save it, and then we'll check.